Hello, Tensor friends. This is the last one in this series on finding the Gaussian Curvature Tensor. Uh, what prompted this whole mess was that I got a new book. It's an old book, but it's new to me, called Riemannian Geometry. And on one of the first few pages of it, it had Gaussian curvature. And I said, well, I don't know what that is, so I need to understand that. But I wanted to do it in a tensor, the format, because I've been studying a tensor calculus for almost a year now. I really love it, by the way. It's a lot of fun. So that's what prompted all this, and that's what we've done. So let's get rocking. In the video, we found this relationship between the covariant derivative of a covariant basis vector is equal to the curvature tensor times the the vector. Okay. Now, what is a basis vector? A basis vector is the derivative of a position vector with respect to a coordinate. Okay. Now, because this position vector here has no indices, we can also write that as the covariant derivative of that position vector. If it had indices, we would have to include the terms for the Christoffel symbols, but we don't because it doesn't have any. Okay, so we can take this and put it right back in here, and now we get two covariant derivatives of that position vector is equal to this. Now, what we want to do is raise the indices by multiplying it times the contravariant metric tensor of the surface. So this is the surface contravariant metric, the tensor. Now, you may not know this, but the covariant derivative of a metric tensor is 0, which means that I can move it inside these operators wherever I want. That's called the metronylic the property. Okay, so when the covariant derivative of something is 0, you can just move it inside here. So I moved it right here, raise this index, and I got this. Okay, now we want to isolate this with the mixed indices, the curvature tensor with the mixed indices. So we dot both sides with this unit normal vector. And you know this is just 1, right? So now we've got it by itself. So it looks like this. Now, what actually is this? Let's look at what it actually means. On our surface, our embedded surface in the ambient space, we only have two coordinates, alpha and beta, which were theta and phi, right? We did that back in video number 1. So since there's only two the coordinates, and this is a 2-index tensor, that means we need to find a 2 by 2. The matrix would be the components of this tensor. So as an example, the theta would actually be the second derivative of this expression with respect to theta squared. Then you have the mix, the phi, the theta, then the theta phi, and then the phi squared. This is actually the format that I found in that very first the few pages of my Riemannian geometry, the book, where Professor Morgan had expressed this is kappa, the Gaussian, the curvature, as this, as a Laplacian of this function, right? So this is now the same as this. So we have found an expression that will give us the Gaussian, the curvature from the tensor, okay? So, but we want this, but we already found this. So we're just going to take this, raise that index again by multiplying it times the contravariant, the surface metric, the tensor. And here is that metric tensor. We found this back in like video number 2. We found this in the video before this one. We multiply those together and we get this. So these are the components of the Gaussian Curvature Tensor, okay? Now, it turns out that to find the Gaussian curvature, kappa is what they call it, of a sphere with constant radius a, we just multiply these together. So it's the determinant of that matrix, and it is 1 over a squared. And that makes sense. Let's look at it. So this is the radius. So for a radius of 2, we get a certain, the kappa, the value. As we lower the radius, gets smaller and smaller, the curvature increases. Well, that makes sense, right? Because the surface of an Earth is the Earth is a sphere, and it has a curvature. It's extremely small, but it has it. So if I set a beer down on the ground, it doesn't turn over. But if I set a beer in a basketball, it's probably going to turn over because the curvature is much, much, much higher. So that's what that means. Now, I also did this problem of finding the curvature of a sphere with a constant radius in Riemannian geometry. First, you have to find your metric, the tensor, g mu nu. Use the metric tensor to find the Christoffel symbols. Use the Christoffel symbols to find the Riemann curvature tensor. You contract the Riemann curvature tensor to find the Ricci curvature tensor. And then you contract this rascal to find the Ricci scalar. And I'll leave a link to this in the description. This was long and intense, but it's a lot of fun. I encourage you to watch this. It's a lot of fun. Now, you notice there, the Ricci scalar for a sphere with constant radius is 2 over a squared. But kappa is of the Gaussian curvature is 1 over a squared. Well, why is it twice? What does that mean? Well, I asked Google AI what it means, and here's what it told me. Ooh, I cut that off. Sorry, it doesn't matter anyway. The Ricci scalar is twice the Gaussian curvature tensor in context of a two-dimensional surface like a curved plane. The Ricci scalar essentially captures the average curvature across all directions. So since kappa was 1 over a, I guess the scalar is just 1 over a in this direction, 1 over a in that direction. So it's twice. I don't know what it means. That's all I can imagine it means. If you understand that and have a better answer, I sure would like to hear it. Okay. Well, that's it. I'm going to go off in a different direction now. Probably study more Riemannian geometry. Don't know where I'm going, but I'll see you later, and thanks for watching.